Welcome back to the deep dive. Okay, so today our mission is all about getting practical. We're looking at Gauss's law.
Right.
Not just the theory, but how we actually use it, turn it into, well, maybe the sharpest tool in the box for electrostatics.
Absolutely. It's about taking this fundamental idea and making it work for us. Electrostatics really boils down to two main laws.
Okay.
There's Gauss's law, which links the electric flux, kind of the flow of the field,
Mhm.
through a surface to the charge tucked inside that surface.
Flux equals charge inside. Got it.
Yep, divided by epsilon naught.
Yeah.
And the second law is that the curl of the electric field is zero.
Which sounds technical, but it basically means the field is conservative, right? You can't gain energy just by moving a charge in a loop and coming back to the start.
Exactly. No free energy from static fields.
Yeah.
But today, yeah, we're zoning in on Gauss's law. Because the real magic happens when you combine it with symmetry.
Symmetry, that's the secret sauce.
It really is. It lets us sidestep some really nasty calculus and solve problems that would otherwise be, well, almost impossible.
So for you listening, the goal here is to see how symmetry unlocks Gauss's law, and, maybe more surprisingly, how the law reveals some deep truths about why classical physics kind of struggles with stability. Let's dive right into one of those surprising truths. Something that feels wrong at first.
Okay.
Imagine you have a single point charge, just floating there. Can you arrange a bunch of other fixed charges around it to hold it perfectly still, like in stable equilibrium?
The short answer? No, absolutely not.
Really? Not all.
In electrostatics, there's no such thing as a stable equilibrium point for a charge sitting in a static electric field created by other fixed charges. You can find points of unstable equilibrium, sure, where the net force happens to be zero right at that point.
But unstable means if you nudge it even slightly.
It gets pushed further away. The field can't possibly provide a restoring force pulling it back from all directions at once. It's fundamentally impossible in a static field.
Huh. Why is that? Is it Gauss's law again?
It follows directly from it. Think about it. If you had a stable point, the electric field lines would all have to point inward towards that point, right, to pull the charge back.
Okay, yeah, like a little gravitational well, but electric.
Exactly. But now, imagine drawing a tiny imaginary sphere around that stable point.
Mm-hmm.
If all the field lines point inward, you have a net inward flux through that sphere.
Right.
But Gauss's law says the net flux is proportional to the charge inside. And we just put our test charge, there's no other charge inside our tiny sphere that's creating the field.
Ah, so zero charge inside means zero net flux. But the inward pointing field lines require negative flux. It's a contradiction.
Precisely. You can't have an inward flux everywhere without having a negative charge inside to source it. Geometry and Gauss's law forbid that kind of stable electrostatic cage.
So even if you had, say, a charged rod balanced between supports, it's never truly stable. The forces can cancel, but not restore from all directions.
That's the idea. The total force might be zero at one point, but it can't be restoring in all directions if it's purely electrostatic forces from fixed sources.
Okay, that instability, it feels like it should have big consequences, like for matter itself, atoms.
Oh, absolutely.
Yeah.
This leads us straight into why classical physics just couldn't explain why atoms don't, fall apart.
Right, the old atomic models.
Yeah, think about the early ones, like Thomson's plum pudding model.
Electrons swimming in a blob of positive charge.
Sort of, yeah. Little negative plums in a positive pudding. But based on what we just said about stability.
Uh-oh. The electron should just head for the center. But there's no stable point there either.
Exactly. There's no point of stable equilibrium anywhere inside that positive sphere, according to electrostatics. The model predicts collapse, or at least oscillation, which just doesn't match the stability we see in real atoms.
Okay, so plum pudding fails the stability test. Then came Rutherford and Bohr with the planetary model, electrons orbiting a nucleus. That seems more stable.
It solved the immediate collapse problem, but classical physics threw up another, even bigger roadblock. Classical electrodynamics, which says any accelerating charge must radiate energy. An electron whipping around a nucleus is definitely accelerating.
So it should be losing energy continuously.
Continuously.
Yeah.
Like a tiny radio transmitter. And if it's losing energy, its orbit decays. It should spiral into the nucleus in like a fraction of a second.
Wow, okay. So both models, viewed through classical electrostatics and electrodynamics, predict atoms should be completely unstable.
Totally unstable. It was a massive failure. It basically proved that you need something entirely new quantum mechanics to explain why matter holds together. Classical physics just can't do it.
So classical electrostatics tells us why atoms should collapse, but not why they don't. That's sobering.
It is. But let's pivot back to where Gauss's law does shine, using that symmetry to actually calculate fields.
Right, the practical power tool part. Solving problems that look impossible otherwise.
Exactly. The trick is choosing the right imaginary surface, the Gaussian surface, that matches the symmetry of the charge setup.
And we pick a shape, not because it's physically there, but because it makes the math easy.
Pretty much. We pick a surface where the electric field, E, is either constant and perpendicular to the surface everywhere.
Okay, so the dot product in the flux integral is simple multiplication.
Or where the field is parallel to the surface.
So the dot product is 0, and there's no flux through that part.
Bingo. If we can manage that with our chosen surface, the big scary flux integral just becomes E times area, basically.
Nice. Let's see the classics. First up, an infinitely long straight line of charge. Uniform charge density.
Okay, infinite line. What's the symmetry?
Cylindrical. It looks the same if you rotate around it or slide along its length.
Perfect. So we use an imaginary Gaussian cylinder centered on the line charge. Now, which way does the E field point?
It has to point radially outwards, away from the line, like spokes on a wheel, but in 3D.
Right. So what's the flux through the flat end caps of our cylinder? 0. The field lines are parallel to the caps, not going through them.
Exactly. So all the flux goes through the curved side wall, where E is constant and perpendicular. You run Gauss's law.
And what do you get for E?
You find that the electric field I level drops off as 1 over R, where R is the distance from the line. $1 propto 1-1.
Whoa, wait. 1 over R, not 1 over R squared like a point charge?
Nope. $1. It falls off much slower. That infinite line's influence stretches out further, in a way. Geometry matter.
That's a huge difference. Okay, next. The infinite flat sheet of charge. Uniform surface charge density, sigma.
Now we have planar symmetry. The sheet looks the same if you move parallel to it.
So the field must point straight away from the sheet, perpendicular to it, on both sides.
Correct. So what Gaussian surface should we use?
Something that cuts through the sheet? Maybe like a small rectangular box? Or a cylinder, like a little pillbox?
A pillbox works great. A small cylinder piercing the sheet, with its flat ends parallel to the sheet. Where does the flux go now? Well, the field is parallel to the curved sides of the pillbox, so no flux there. It only goes through the 2 flat end caps.
Exactly. And because the sheet is infinite, the field strength E should be the same no matter how far the caps are from the sheet. It's constant.
Constant. The field doesn't drop off at all.
Not for a truly infinite sheet. The calculation gives we deal a sigma 2 epsilon dollars. Constant magnitude, independent of distance.
Mine. Blown. Okay, that's wild. What if we put 2 sheets together? Parallel, close, but with opposite charges. Like plus sigma and A to sigma.
The capacitor setup. Now you use superposition. Outside the 2 plates.
The field from the positive sheet points away. The field from the negative sheet points towards it. They're equal and opposite. They cancel.
They cancel perfectly. 0 field outside, but between the plates.
The field from the positive plate points towards the negative one. The field from the negative plate also points towards the negative one. They add up.
They add up. And you get a constant field E equal to sigma epsilon dollars. Double the field of a single sheet, perfectly uniform between the plates, 0 outside. That's the ideal capacitor.
Very cool. Okay, one more major shape. The sphere. Perfect spherical symmetry.
The sphere is crucial. Let's say we have a solid sphere of radius r, with charge distributed uniformly throughout its volume.
Okay. Symmetry demands the field must point radially outward, right? And its strength can only depend on the distance r from the center.
Absolutely. So naturally, we use a spherical Gaussian surface centered at the origin.
Case 1. Our Gaussian sphere is outside the charged sphere, so its radius r is greater than r.
Right. What charge is enclosed by our Gaussian surface?
All of it. The entire charge of the sphere.
Correct. And because of the symmetry, Gauss's law essentially says, from the outside, this sphere acts just like all its charge was crushed down into a single point at the center.
So we get the familiar point charge result, Taralar is proportional to 102.2.
Exactly. Outside a uniformly charged sphere, the field is identical to that of a point charge at its center, carrying the same total charge. 1 propto 1 or 2.
Okay, but what about inside? Now, our Gaussian sphere has radius r less than r.
Now things change. How much charge is enclosed by this smaller Gaussian sphere?
Only the charge within that smaller radius r. Since the charge is uniform, the amount should grow as the volume grows. Like $303.
Exactly. The enclosed charge is proportional to 3r12. The surface area of our Gaussian sphere is still 4 R22. You plug those into Gauss's law.
Let's see. Field times 22 is proportional to 303. So E must be proportional to just R.
You got it. Inside the uniformly charged sphere, the electric field E is 0 at the very center of Gaussians and grows linearly with distance r until it reaches its maximum value at the surface. All del, prepto or on.
Wow, completely different behavior inside versus outside. 0 at the center, linear increase, then 102.3 dis K. That's neat.
It really is.
Yeah.
And this leads to another fascinating conceptual point. We usually think of Gauss's law using the 102.2 nature of Coulomb's law.
But you're saying it goes the other way, too. Gauss's law can actually test how good that 102.2 law is.
Precisely. It's deeply connected to the geometry. Gauss's law works mathematically because the area of a sphere grows exactly as 20 $, which perfectly cancels the 102 decay of the field from a point charge. The flux depends only on the enclosed charge, not the size of the sphere.
Okay, so if Coulomb's law wasn't exactly 102.2, if it was like 1r2.000000 as well,
then the cancellation wouldn't be perfect. The whole mathematical structure of Gauss's law would break down slightly. The flux would depend on the surface, not just the charge.
How on earth could we test such a tiny deviation?
We use the property we derive for the sphere, but apply it to a hollow shell of charge. If Coulomb's law is exactly 102.2, then the electric field inside an empty, uniformly charged spherical shell must be perfectly, absolutely 0.
Why 0?
Because the contributions from the charges on opposite sides of the shell, one closer but smaller in apparent area, the other further but larger in apparent area, cancel out perfectly only if the force law is exactly inverse square.
It's like this perfect balance. If the exponent was slightly off, the cancellation wouldn't be exact, and you'd get some leftover field inside the shell.
Exactly. So the experiment is, build a conducting sphere, which acts like a charge shell, charge it up, and then very carefully measure if there's any electric field inside.
And people did this.
Oh, yes. Famous experiments, like by Plimpton and Lawton, they used incredibly sensitive instruments inside a conducting sphere.
And the result?
0 field. To an astonishing precision, they basically showed that if the exponent deviates from 2, that deviation, often called epsilon, has to be less than something like 1 part in a billion.
1 part in a billion? That's insane. So Gauss's law isn't just useful, it's like a precision tool for verifying the fundamental force law itself.
It's one of the most precise tests we have for the form of Coulomb's law.
Incredible. Okay, let's switch gears slightly. Let's talk about conductors. Materials packed with electrons that are free to move.
Right. Metals, typically.
What happens to the electric field when charges in a conductor finally settle down, reaching electrostatic equilibrium?
Okay, when everything stops moving, 3 key properties must hold for any conductor. First, and most importantly, the electric field, $8 must be 0 everywhere inside the bulk material of the conductor.
Why 0?
Because if there is any field inside, the free charges would feel a force, FQE, and they would move. They'd keep moving, rearranging themselves until they canceled out that internal field completely. So, in equilibrium, E must be 0 inside.
Okay, EO inside. What else? What about any excess charge I put on the conductor?
That leads to the second property. Any net charge placed on a conductor resides entirely on its surface. None stays inside the bulk material.
Is that just because the charges repel each other and push as far apart as possible, which is the surface?
That's the intuitive idea, yes. But the more fundamental reason goes back to Gauss's law in property 1. Since E is 0 everywhere inside, draw any Gaussian surface you like as long as it's completely within the conductor material. The flux through that surface must be 0, because E is 0 on the surface. And if the flux is 0, Gauss's law says the net charge enclosed by that surface must also be 0.
So there can't be any net charge anywhere inside. Any excess charge has to be sitting right on the boundary, the surface.
Exactly. And the third property deals with the field right at that surface, just outside the conductor.
Okay.
The electric field just outside the conductor must be perpendicular to the surface at every point.
Why perpendicular?
Same reason as before. If there was a component of the E field parallel to the surface, charges on the surface would feel a force along the surface, and they'd move. Since we're in equilibrium, they aren't moving, so no parallel component. E must be normal, perpendicular to the surface.
Makes sense. And can we know how strong that field is?
Yes. By applying Gauss's law to a tiny little pillbox, half in and half out of the surface, you find the magnitude of the electric field right at the surface is E d sigma epsilon dollars sigma dana, where sigma is the local surface charge density right there. The field is stronger where the charge is more crowded.
Got it. E outside, charge on surface. E perpendicular outside with magnitude sigma over epsilon naught. That covers conductors.
Pretty much the essentials for electrostatics.
Which brings us to maybe the ultimate application of these conductor properties, the idea of electrostatic shielding. A hollow cavity inside a conductor.
Ah, yes, the Faraday cage effect. This is really powerful. If you have a conductor, could be any shape, and it completely encloses an empty region, a cavity with no charges inside it, then the electric field inside that cavity is guaranteed to be exactly zero.
Wait, zero, even if I bring huge charges outside the conductor or change the shape of the conductor?
Doesn't matter. As long as the cavity is empty and completely surrounded by conducting material, the field inside that cavity is zero, period. The conductor perfectly shields the inside from any external static electric fields.
How does that work? The external field lines just stop at the surface?
Essentially, yes. The charges on the outer surface of the conductor rearrange themselves instantly to terminate any external field lines, ensuring E remains zero inside the conductor material itself. And because the curl of E must be zero, the field is conservative, this guarantees the field must also be zero throughout the empty cavity. The potential inside the cavity becomes constant.
So you're completely isolated from the electrostatic chaos outside.
Completely shielded. It's a direct consequence of the properties of conductors and Gauss's law. The inside is totally independent of the static charges outside.
Okay, let's wrap this up. Looking back, Gauss's law is way more than just an equation.
Absolutely.
We've seen it transform into this incredible practical tool. It dictates the geometry of fields, explains why classical physics couldn't handle atomic stability, and even lets us test fundamental laws with mind-boggling precision.
Yeah, the key takeaways really are, first, that hard truth about no stable equilibrium in pure electrostatics. Second, the power of symmetry, choosing the right Gaussian surface, lets us find those $1 constant and 122 fields for lines, sheets, and spheres almost trivially.
And the conductors.
And the rules for conductors. E0 inside, charge on the surface, leading to that perfect shielding inside a cavity. And underlying it all, that astonishing confirmation of the 122 law from the zero field inside a shell.
That precision test is still kind of blowing my mind. The idea that if the exponent wasn't exactly 2 even by 1 part in a billion, the way fields cancel, the structure of atoms, everything would be different.
And fundamental. Which leads to a final thought to maybe ponder.
Go on.
We know Coulomb's law holds incredibly well at everyday distances and even down to atomic scales. But what about at really tiny distances, like inside the nucleus? Or in enormous cosmological scales? Are there ongoing experiments still pushing the limits, trying to see if that perfect $1 behavior holds everywhere, under all conditions? What would it mean if we found a tiny deviation?
Something to think about, indeed. Thanks for joining us on this deep dive.